Great. And so, yeah, in order just to try and get back on schedule, let's get started straight away. So Eoin O'Connor today will tell us about action quantum speed limits. Please take it away.
Great. Thank you, Paul. Big thanks to the organizers for giving me this opportunity to speak. So today I'm going to give a brief overview of quantum speed limits and demonstrate the advantages of our new kind of quantum speed limit, which we call action quantum speed limits. All right, I'm going to start by considering something I'm sure you're all familiar with, which is the Heisenberg uncertainty relation, which in its original interpretation suggests that the position and momentum of a quantum particle cannot be measured simultaneously with infinite precision. And then only a couple of years after that, the American mathematician Robertson showed that simply by applying Cauchy-Schwarz inequality, you can get this kind of more general relationship between the variance of two quantum observables and their commutation relation. So if we just take this relation and we apply it to position and momentum, out pops this kind of more exact version of the position, momentum, and uncertainty relation. Unfortunately, it's not so easy to apply this bound to the energy-time uncertainty relation because in general, time here cannot be represented as a quantum observable. So we need to come up with a different strategy to get a more exact energy-time uncertainty relation. So this is where quantum speed limits come in. So in 1945, Mandelstam and Tamm introduced this kind of new exact interpretation of the energy-time uncertainty relation, which you can see here. So in this form, the time is no longer really associated with a measurement or simultaneous measurements, but it's kind of an intrinsic time scale of the system we're considering. And then there wasn't too much work in this area for like over 50 years, but then Margolis and Levitin showed up and they kind of asked a different but related question, which is like, what is the minimum time required to transform an initial pure state into an orthogonal one? So we might want to make this transformation for measurement purposes or for computational purposes. And they ended up with this band here, which is very similar to the Mandelstam band, but instead of the energy variance, we now have this average energy term. That's the only difference. So since there's no real strict hierarchy between the two bounds, the convention of the literature is to use this unified bound where we take the maximum of the two bounds and consider that to be our bound. Also, you can generalize the Mandelstam band to non-orthogonal states and to time-dependent Hamiltonians. So we just get this like Buer's angle and a time average integral of the variance here. So then the next logical step after these generalizations would be to consider mixed states. So there are many ways in which this problem can be approached, but the one I'm going to focus on is these geometric quantum speed limits. So these bounds use the fact that in any given metric, the path length always has to be larger than the geodesic distance between the start and end points. So if we kind of multiply both sides by time and do some rearranging, we can kind of force this to be a bound on time, like so. Unfortunately, for mixed quantum states, there's kind of infinitely many suitable metrics, each with their own geodesic path and each giving different quantum speed limit times that we can apply to this bound. So it's really not clear what the correct metric is to choose in any given situation. It's worth noting, I guess, for pure states that this is kind of a geometric bound itself, but there's only a unique metric that can be used here, and it's related to the Fisher information metric and the Fubini study metric, and it derives this bound here, this generalized Mandelstam bound. So yeah, how can we decide which bound to calculate, or how can we make sense of this infinite family of bounds? And kind of one way I like to think about this issue is using this kind of explanation of Snell's law you might have seen before. So basically the idea is you have a lifeguard on the beach, and then there's somebody here in the water who's drowning. So the lifeguard wants to get to the drowning person as quickly as possible to stop them from drowning. So they might initially think, oh, I should run directly in a straight line to get to the person, but that's not necessarily the fastest way to get there, because the lifeguard is faster at running on the sand than they are at swimming in the water. So they would want to maximize the distance they cover on the land before entering the water. So they would follow this bottom red path here. But you could think of the same problem if the lifeguard happened to be, say, a sea turtle. In that case, following this red path would be even worse than going in a straight line, because the sea turtle is a faster swimmer than it is moving across the sand. So the sea turtle would follow this green path up here. And again, if it was a butterfly doesn't care whether it's got sand or water underneath it, it just flies in a straight line there. So that's going to be its best path. So kind of, if we want to take this back to the picture of our quantum speed limits, kind of goes to highlight that the best path between any 2 points in our system is going to depend on who you're asking, or in our case, like what metric is relevant in this case. So if we think back to the unitary case from earlier, maybe if we wanted to minimize the energy variance in our system, we would want to minimize the Mandelstam bound, or if we cared more about the average energy in our system, we would use the Margolis-Levitin bound. So to highlight some of these points, we looked at the case of a qubit thermalizing in contact with a bath. So this is described by a generalized amplitude damping channel. And the path that this channel takes for a qubit is shown in the block sphere here by this dotted red line. And then the 3 other lines you see are 3 examples of geodesics for different metrics. So this green line here is related to the quantum Fisher information metric. The purple line is related to the Wigner-Yanasi skew information metric. And this straight line here is a geodesic in the trace distance metric, which just comes from this simple bound here. And then, so what we've done here is we've plotted the quantum speed limit times for various different pure initial states. That's what theta denotes. You can see that there's no strict hierarchy between among the bounds. Each of them are tightest at various different times. So this just kind of goes to show that it's more of a notion of the optimality of the path, how close it happens to be to the geodesic, rather than some kind of minimal time we can abstract. So if we look at kind of the general construction of these geometric quantum speed limits, we notice a few peculiar features showing up. So the first would be that this bound really only depends on the average speed along the path, as opposed to the instantaneous speed in any way. If we look at the denominator here, it's just the time average path length. But the instantaneous speed is of fundamental importance in many areas of quantum physics, from the thermodynamic performance of engines to dynamics across quantum phase transitions. Additionally, kind of these quantum speed limits really force the inequality to be on time, whereas like what we really have is an inequality on length, saying that the path length is greater than the geodesic length, and we force it to be on time by multiplying both sides and rearranging. So I think both of these together go to show, as I said, it's more of an indication of optimality rather than necessarily an achievable minimal time in the system. So we attempt to address some of these shortcomings by introducing a new family of quantum speed limits, which we call the action quantum speed limits. So we start by considering the Cauchy-Schwarz inequality here, and we just choose one of the functions to be a constant, or in this case 1, and the other function is going to be basically the instantaneous speed in the metric g that we choose. So subbing this into the inequality, this term here, so we're integrating over the instantaneous speed, that gives us the path length. squared, which is going to be greater than or equal to the geodesic distance squared. And then on the left-hand side, we denote this term here to be the action along the curve. And here we see that the time kind of appears more naturally here coming out of this integral. And simply rearranging, bringing this over here, we get that the time is going to be bounded by the square of the geodesic distance divided by the action. And yeah, we see that the time no longer explicitly appears in this equation, which is a bit of an advantage. So this derivation might look a little bit familiar to some people, as it's kind of closely connected to the ideas of thermodynamic length and dissipated availability from classical thermodynamics. So I believe that there's some scope to connect these speed limits to quantum thermodynamics, especially to quantities such as the entropy production. And we see that we have this relationship between any given geometric speed limit and the corresponding action quantum speed limit. So although we solved some problems, we still have infinitely many action quantum speed limits as well, which doesn't inherently help with narrowing it down. So then you have the problem of, well, how do I saturate this bound? If I have the bound, how do I actually get there? So in order to saturate this bound, what you have to do is you follow the geodesic path and you move at a constant speed along that path in the corresponding metric. And this is kind of equivalent to minimizing the action along the path. And this is a common problem in classical control theory. So we have some external control parameters and we want to find a time-dependent value of those parameters that minimize the action. So once again, we use the example of a qubit thermalizing with a bath. We have these plots. So here, this blue line is just the geometric quantum speed limit that we saw in earlier plots. And this is for all possible ramp profiles, P of t, going from an initial pure state to our final thermal state up here. And so the geometric speed limit is going to be independent of whatever the ramp profile is. But the action quantum speed limits are sensitive to this degree of freedom. So initially we sub in this kind of naive linear ramp here in green, and we see that our action quantum speed limit is not tight. We're actually, quite far off in certain places. Then we apply the optimal control, and we get up to these red dots here. So we're able to saturate that Cauchy-Schwarz inequality and basically do as well as we possibly can. Then over here, you see some examples of what those optimal ramps are for various different initial states here. So this just corresponds to different values of theta over here. So that example there was for the trace distance metric, but we can apply this to basically any metric. And so here we've done it for the quantum Fisher information metric as well. So we get the same setup. We see that for our initial guess, we're not able to, we're kind of quite suboptimal. We apply the optimal control and we saturate the Cauchy-Schwarz inequality again. And then we have additional examples of what those optimal ramp profiles are, and they're actually quite different between the trace distance metric and the quantum Fisher information metric, which is kind of interesting. So yeah, if you want to learn some more about anything you've seen here, you can check out the paper. The reference is just here at the bottom. Kind of the main conclusions. So all geometric speed limits are saturable simply by following the corresponding geodesic path in whatever metric you're considering. So taking the maximum over all of these quantum speed limits, like you would do in the unitary case, is not very productive. The best speed limit is going to depend on the situation or the system at hand. The instantaneous speed is very relevant in a lot of areas of quantum physics, and this degree of freedom is less relevant to geometric quantum speed limits, as they only depend on the average speed. As I've just shown, these action speed limits are well suited to optimal control techniques, as there's a lot of work already done in the classical setting. And in my opinion, kind of the goal going forward for the field of quantum speed limits would be to find more physically relevant quantum speed limits, rather than always just looking for a tighter bound than the previous one, because as I've shown, all of these things are saturable in certain conditions. So yeah, big thanks to Steve and Giacomo for working on this with me and guiding me through the project. And yeah, I don't know if you have time for questions, but thank you anyway.
Thank you very much, Owen. That was also very nice and clear and interesting. Yeah, we do have I mean, you finished quite early, so if there are any questions, please do pop them in the chat now. I can't see none have popped up just yet, but I guess while we're waiting for a couple of minutes for them to come up. Oh, hello. Okay, there is one question just coming in from Maximilian Locke. I'll just wait, give him a chance to type. Or unless you want to ask with your microphone, please go ahead.
Actually, maybe easier. Thanks. Yeah, thanks for this really interesting talk. I didn't really get, I suspect because of the short time of the talk, I didn't really get when you then consider, you introduced action speed limits as a way to generalize from pure state, but I didn't really get what then changes in that case. Can you elaborate on that a bit?
To generalize from the geometric speed limits, or? Sorry,
yeah.
I didn't, you broke up a little bit. I didn't quite get the middle.
Sorry, I had a bad internet connection. Yeah, my question was, if I understood correctly, the introduction of action speed limits, the benefit of it is that it's somehow easier to then deal with open systems or with non-pure states, right? Did I misunderstand that?
So I guess the benefit, the way I see it, is you have kind of, the benefit is in how you would choose which metric to consider, right? So basically you have this quantity kind of on the bottom of your speed limit, which you end up kind of wanting to minimize. So here you want to minimize the path length, so you want to get as close to the geodesic distance as possible. Or here you want to minimize the action, right? And I think it's kind of, the action here is a more physical thing, right? Because it depends on the instantaneous speed. You can sometimes relate it to things like excess entropy production and stuff. So what it means to minimize an action quantum speed limit has a more physical meaning than what it means to follow the geodesic path necessarily. And so that's what I hope to, yeah, that's what I think the benefit of the action quantum speed limit is, kind of more physical relevancy. But yeah, maybe I didn't emphasize that as much. I hope that makes some sense. But already the geometric speed limits work for open quantum speed limits, but I'm trying to make more physically relevant limit or quantum speed limits, I guess is the idea.
Okay, thanks.